Okay, imagine you send a message in a bottle out into the cosmic ocean, a map, leading back to us. But what if one of the lighthouses you used to draw that map had a secret? That's what we're digging in today. A very special star that's part of humanity's greeting to the galaxy, and the incredibly strange, ghostly hum it's been making.
Way back in the 1970s, we launched the Pioneer probes. We sent these things out into the absolute vastness of space. And on them, we attached these messages, these little cosmic greeting cards from Earth, hoping that maybe, just maybe, some intelligent life out there might find them one day.
So this plaque, it's basically a cosmic map, but instead of using regular stars, it uses something much cooler, pulsars. You can think of them as these incredibly precise cosmic clocks, each one with its own unique pulse rate. The plaque uses 14 of these to triangulate our position. And one of those absolutely critical landmarks, our little signpost, is a pulsar called B0525+21, chilling out 6,500 light-years away. For decades, we thought we knew this star. Turns out, we really didn't.
All right, so to really get why this is so weird, we first got to understand what a pulsar even is.
The best analogy is a lighthouse. You've got this super powerful beam that just sweeps around and around. When that beam hits you, you see a flash. When it's pointed away, you see darkness. That flash, astronomers call that the on pulse, and the darkness in between is the off pulse. For pretty much any normal pulsar, we expect to see a powerful blast of radio waves, the on pulse, and then total radio silence, the off pulse. Simple, right? Well, not for B0525+21.
This whole thing is a detective story that's been playing out for years. It all kicked off back in 2011 with a really surprising observation. That led a new team to take a much closer look in 2017. But what they found a couple years later? It didn't solve the puzzle at all. It just made things way stranger. So back in 2011, a team led by Rahul Basu used the giant meter-wave radio telescope, the GMRT, to take a good long look at B0525+21. They were trying to carefully separate that on pulse from the off pulse, and they knew exactly what they were supposed to find: a really strong signal during the flash, and then absolutely nothing during the silence.
And sure enough, they found the on pulse, right on time. A nice, strong signal of about 80 millijanskis. That's just the unit they use to measure this stuff. But then they looked at the data from the off pulse, the part that was supposed to be completely dead silent. And it wasn't. There was this faint but definitely real radio signal, a persistent little hum where there should have been absolute nothingness.
The strength of that hum came in at 3.9 millijanskis. Now, that might sound tiny compared to the main pulse, but its existence was a huge problem. The standard models for how pulsars work have zero explanation for this. It kind of suggested that this emission was coming from outside the main beam, maybe from the pulsar's wider magnetic field, its magnetosphere. This was a wild idea that basically threw a wrench in everything we thought we knew.
So, a discovery this big, one that challenges the textbooks, yeah, you better believe it needs to be verified. So a new team of scientific detectives decided to reopen the case, but this time they brought in a much more powerful instrument to get a closer look.
This new tool was the European VLBI network, or EVN. Now, this isn't just one telescope, it's a whole network of radio telescopes spread all across the globe, and they all work together. The result is basically an unbelievably powerful cosmic zoom lens. It can see details with a resolution that just blows the GMRT out of the water.
So the new team, led by Benito Marcote, was ready to go. They aimed their incredible zoom lens right at B0525+21, ready to finally confirm this mysterious hum once and for all.
And just like the GMRT, the EVN saw that main on-pulse perfectly. The lighthouse flash was there, bright and clear, no problem. So, the first part of the original discovery was confirmed. Now for the really crucial part, that off-pulse hum.
But when they crunched the numbers from the off-pulse phase, there was nothing. Just silence. The signal that the GMRT had definitely detected was, according to this even more powerful telescope, not there. The hum had literally vanished.
This created an absolutely mind-bending paradox. The 2011 study was solid science. The 2019 study was also solid science. Both telescopes were working perfectly. So how? How could a signal be clearly detected by one telescope and be completely invisible to another?
The answer wasn't some mistake in the lab.
The answer was all about what these two very different telescopes were designed to see. It was, in a way, a kind of astronomical illusion.
Okay, so here's the key difference. The GMRT, it's like a wide-angle lens on a camera. It's fantastic at picking up big, faint, kind of spread out things. The EVN, on the other hand, with its telescopes all over the planet, that is a powerful zoom lens. It's built to see tiny, sharp, little points of light with incredible detail.
And that's it. That's the solution. The hum wasn't gone at all. The EVN's super powerful zoom was so focused on seeing a tiny little point source coming from the pulsar itself that it completely missed the bigger picture. The source of the hum was so large and spread out that the EVN's sharp vision just filtered it out. It made it totally invisible.
So let's just lay out the case file. The GMRT, with its wide-angle view, saw the hum. And, assuming it was a small source, they concluded it must be coming from the pulsar's magnetosphere. Then, the EVN comes in with its zoom lens and sees nothing. And that proved the emission was not from a small, compact source. It had to be something much, much bigger.
So this discovery basically pointed the finger away from the pulsar itself and out into the space around it. And the main suspect for what's causing this hum? Something called a pulsar wind nebula. You can think of a pulsar wind nebula as basically the exhaust cloud from a pulsar. The pulsar is constantly shooting out this wind of super-fast particles. And when that wind slams into all the gas and dust just floating around in space, it can create this shock wave that starts to glow, and that glow produces radio waves. So here's where we've landed, at least for now. That mysterious hum is most likely a really faint and pretty compact pulsar wind nebula. As B0525+21 zips through the galaxy, it's creating what's called a bow shock, kind of like the wake a boat makes as it pushes through water. This glowing nebula is tiny on a cosmic scale, but still way too big and spread out for the EVN zoom lens. But it's just right for the GMRT's wide-angle view to pick up.
And so, one of the 14 lighthouses we used to draw a map to our home, a beacon for any potential alien civilization to find us, turns out to have this whole other secret. It's not just some simple, predictable flashing light. Nope, it's a complex engine, dragging its own glowing cloud behind it as it tears through space. It's just an amazing reminder that even when we think we have a clear map, the cosmos always has more secrets to show us. The case isn't closed, and you can be sure this investigation is far from over.